Our next presenter is Douglas Wallace from the Department of Oceanography at Dalhousie University. Doug is an oceanographer who uses observations of chemical distributions to unravel the complex biogeochemical process that connect the ocean and the atmosphere. He introduced several approaches and tools that have had long-lasting impact on our understanding of marine biogeochemistry and its connection with climate, especially with respect to the uptake of carbon dioxide and oxygen by the oceans.
Good morning, good afternoon to everybody. This is just such an interesting and varied session, and we're going to shift gears once more time and head to the ocean. And I'm sure most of you are aware that the ocean is one of the main reasons for making Earth a habitable planet. And one of the main reasons for that is that the ocean breathes. It exchanges gases with the atmosphere. And that's one of the key aspects of our research at Dalhousie University. A quick word of warning. We're going to go fast in this presentation, very fast. So I think you're familiar, well, we're all familiar with human breathing. We breathe in oxygen, we breathe out CO2. We can say that our breathing is biochemically driven. It's driven by respiration, and our lungs play a role, and our bloodstream delivers the gases and recovers them from the extremities of our body. And ocean breathing is a little bit different. It's driven by both biochemistry, but also by temperature changes, because temperature controls the solubility of gases. And the ocean doesn't only respire, but it also, there's photosynthesis in the ocean because of light, which segregates photosynthesis and respiration. And the equivalent of our bloodstream in the ocean is the ocean circulation. And these processes lead to exchange or breathing in and out of gases at different places at the ocean surface and at different times on a global scale. For example, you can see outgassing of CO2 in the tropics and ingassing in high latitudes, including in the Labrador Sea. We see something very similar for oxygen. Again, different locations, either releasing oxygen to the atmosphere or breathing it in. And again, you can see a role for the North Atlantic, the Labrador Sea, breathing in oxygen. So how do we know this? Well, we've been measuring oxygen in the ocean for well over 100 years from research vessels. But increasingly today, we're using robots because we can collect a lot more data in a lot more locations. For example, these profiling floats, which move up and down in the ocean about every couple of weeks, between the surface and 2,000 meters. And they can measure oxygen now along the way. And together with colleagues, I was one of the first to actually do this type of deployment of this type of robot in the Labrador Sea. And what we found was we saw an enormous increase in oxygen between summer and late winter conditions as surface waters mixed down into the deep sea, down to a depth of 1.5 kilometers. And the oxygen increase was driven by breathing in big gulps of oxygen coming in from the atmosphere. A place like the Labrador Sea, there's only a few such places like it globally, where the surface water in the atmosphere communicate directly with the deep ocean. And they act sort of like lungs for the deep sea. And then the equivalent of our bloodstream is the deep ocean circulation, which carries the oxygen from the lungs of the ocean into the extremities, just like blood carries oxygen from our lungs to our fingers and toes. The reason this matters is because, in contrast to the situation on the continents where animals generally have enough oxygen all the time, there are places in the ocean where oxygen concentration becomes so low that it can pass a tipping point or threshold where life itself is threatened. And it's not just a life or death situation, but it's also a habitat control. For example, for this blue marlin, as the yellow line on the figure there shows the diving depth of this satellite-tracked marlin, you can see that it was avoiding the very low oxygen concentrations, but dove much deeper where oxygen was plentiful. The breathing matters also because the ocean has taken up over the past 200 years a vast amount of the extra CO2 we've released into the atmosphere by burning of fossil fuels. And if you put a value on that right now, if we took the Canadian carbon price, we'd estimate the value of that ecosystem service as almost $500 billion per year globally. Of concern, however, is that this breathing, we believe, is subject to change under climate change. And this is an example of the change projected change by the end of this century of the oxygen uptake, showing especially very large decreases in uptake in the North Atlantic in places like the Labrador Sea. And part of that's due to surface warming, which makes surface waters less dense and prevents them mixing deep, but also, especially in eastern Canada, the effect of increased freshwater might be a major factor arising from the melting of, for example, the Greenland ice cap. So in our group at Dalhousie, we're actively measuring that, especially in the Labrador Sea, using a pretty unique device, which we call Sea Cycler, which we use to really measure the breathing of the sea. And so what this is, it's an underwater winch, which raises and lowers a float, which has a lot of sensors on it, to the surface, collecting profiles for a year, measuring profiles about every 4 times a day for a year. And you can see this underwater winch is really large. And it's large partly because it has to withstand the extreme conditions which we experience in the Labrador Sea. You wouldn't want to be there on a ship. What it does is that it collects time series of a large number of parameters, for example, oxygen, CO2, and nitrate, nitrate being a key nutrient. And from that, we can examine in detail the breathing process. For example, the breathing in of CO2 and oxygen with the exchange with the atmosphere. When we do that, we see oxygen breathing is in blue and CO2 breathing is in purple. And we can see oxygen being breathed in the winter, but very variable from day to day, depending on things like wind speed, and CO2 being breathed out, being breathed in the spring. And that's got to do with biological uptake and photosynthesis in spring. We can use the data from the Sea Cycler at very high resolution to test our understanding of how this process works, and especially test whether we understand it well enough to incorporate it into models to project the future. And what we found is that we don't fully understand this process. And especially, we think the uptake of oxygen by the Labrador Sea in wintertime is probably pretty seriously underestimated with some of the ways we estimate it. And that's maybe not surprising, given the complexity of the processes operating there, especially the role of bubbles in this breathing process, which is extremely difficult process to study in the lab, for example. You have to study in the field, which is why we developed Sea Cycler. And I just want to finish now with thanking my collaborators at Dalhousie, Memorial University, and Fisheries and Oceans Canada, at Scripps in California and Guillemar in Germany, especially the team at Dal of engineers and scientists who worked on the getting the equipment in the water and processing the data. Thanks very much.